discussion of free lunches is more pleasant. But, okay. So now what's our way to study this long wall crossing function? So again, here is a picture, and I only draw essential walls, maybe like such. So we have some point lambda here, and we want to go to lambda minus. And what we definitely want to do, we want to decompose the long wall crossing function into short ones, like such, such. Yeah. 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 Let's make it longer. What? Okay. All right, let's discuss this after the lecture and with camera switched off. Then we can share our experiences. And meanwhile, we are going to decompose the long wall crossing function into a composition of short ones. So a short wall crossing function is just the guy who intersects a single wall. And so I have like so long WC, the composition of short ones. And what we need to study, we need to take an irreducible module and understand the homological shift. The homological shift is this number I defined by these conditions. We want to understand homological shift for a given module. So want to understand shift of some module M. Now let me make a statement which doesn't make sense. So this shift should be equal to the sum of shifts of M under the short functors. So you kind of have a composition of functors. So the first functor shifts your object by 2, then the second functor doesn't shift it at all, the third functor doesn't shift it at all, and the fourth functor shifted by 5. Your total shift is 7, right? 2 plus 5 equals to 7. Now, unfortunately, it doesn't make sense as stated because the functor will just produce a complex out of a module. And what would we mean by shifting an object? But somehow, on each step, by applying a short wall crossing function, you will still have a distinguished simple constituent in the top homology that appears. And then we are speaking about shifting these top constituents. So one can make sense of this, although it's not so straightforward. So in other words, you need to prove something before this will make sense. But that's somehow a guiding principle. And this guiding principle tells us more or less that it's enough to understand short wall crossing functions, which should be easier. So let me call.
Isn't there no homological dimension of a functor?
I'm not sure. Maybe there is. But so this is like, let me call it informal principle. So this informal principle allows us informal principle reduces the problem
Just crossing the word.
to study shifts under short-wall crossings. And the hope is that short-wall crossings are easier to understand than the long one. So that's one idea. Now there is still a precise statement that we are going to prove. So we need to prove that L omega A lambda nu coincides with the image of the characteristic cycle map. Or maybe a little bit better, that this whole space coincides with the sum of images. Now, assume that this is not so.
So we finished with upper bound, and now
We are finished with lower bound, now we are doing upper bound, so assume that this inclusion is strict. And so, if we were dealing with a problem which could be solved just using representation theory, so how we would like to show that this is nonsense? Well, we would say that there is a singular, there is a singular vector for A lambda in the quotient of the direct sum of the images of CCs modulo L omega A lambda. Actually, in the world of the usual representation theory, integrable representations of A lambda are just completely reducible. So we could just take just some direct complement. Now, obviously this implication is true, but as stated, this doesn't seem useful, right? However, what we need to do in our story, we need to use some argument of similar nature. So we should say that we want to pick an object M. So this is irreducible, finite dimensional, which is singular in this quotient. In particular, this would mean that this characteristic cycle of this object will be singular, but this means more. So one needs to use a more technical definition. So basically, this would mean that CC of M is singular. But again, the definition is more technical than this. And what can be shown about this object so
Is it clear from some general considerations that it is. So the whole model is integrable with, I mean, the whole
Yep.
model is integrable with respect to a lambda.
So now one can show that WCs through real walls meaning walls like Ker alpha with alpha real just don't shift this object M. Or more precisely, you start applying these wall-crossing functions to M, and you always have something in the zero homology. And I would just want to say a sentence how this is proved. This is proved from relation between this wall-crossing function and categorical simple reflection. Simple reflection defined by functors E alpha and F alpha. And again, I don't want to go into an explanation of how this works, but I just want to relate this to the usual representation theory. So suppose that this works like the following, like as follows. So somehow I should have warned you before, but in the remaining 30 minutes, I'm going to give an exposition of some 30 pages of very technical proofs.
Where are those 30 pages found?
From my paper with Bezrukavnikov, and some other papers, another paper of mine as well. So in any case, I'll suppose that you have a vector M in some SL2 representation. And suppose that E of M is equal to 0, right? Now, how do we write what is a simple reflection? It's something like f of k over k factorial minus f of k plus 1 over k plus 1 factorial e plus f of k plus 2 over k plus 2 factorial e squared over 2 minus and so on. Right? So that's a formula. And once this object is singular, so this E of M is singular, so S of M is very easy to compute. It is just f of k over k factorial times M. And f of k over k factorial will give you a bijection between the weight spaces. And that's a very easy bijection. It's very easy to write its inverse. The inverse will be given by ek over k factorial. So basically, this is established by trying to do something like this, but on the categorical level. And again, it is technical. So I'm going to skip any other details. But
So the actual problem is that for imaginary walls, you don't have the construction via two cosmology.
yeah, I should have a construction via categorical Heisenberg action, but this is very, very far from being established. So the question now All right. So now M is finite dimensional. It's not shifted by real short-wall crossings. But the long-wall crossing shifts it by 1/2 of the dimension of the Q over H. So how can this happen? This can only happen if the remaining short-wall crossing functor does the job. Just does the full shift. So from here, you sort of deduce that. So first of all, now if Q is finite, we are done. Because in the finite type, obviously, all roots are real, and that's it. Now suppose that Q is affine, and ker delta is essential. Then, well, wall crossing through ker delta shifts M by this number. And here is a theorem that this short wall crossing functor just cannot have this homological shift. So all homological shifts by this functor are less than half of the dimension, strictly less. So all homological shifts by WC through ker delta are strictly less than this number. And so I arrive at a contradiction. So I'm going to spend the remaining 25 minutes discussing this phenomenon. And I want to start with a geometric reason for this to happen. And the geometric reason for this to happen is the following. So I want to consider the classical Q over H M lambda V. And of course, if lambda is generic, then this guy is smooth, well, and affine. Okay? Now, what happens if lambda is generic on ker delta? Generic would mean Zariski generic. In this case, or you can say that lying of finitely many hyperplanes. This variety is singular. But all singularities are non-isolated. So the point is, if you have a point on this Q variety, then you can describe its formal neighborhood in terms of a smaller quiver. And in this case, so maybe I should state a precise theorem. So semi-precise theorem. So let X in M 0 lambda V be a point. Then the formal neighborhood, the formal neighborhood of this point inside of the Q variety, M lambda 0 V, well, maybe I should write Q W completed at X. So this is formal neighborhood. Formal neighborhood is isomorphic to formal neighborhood of 0 for a smaller Q variety. So this is kind of smaller data. And this is a consequence of what one can call symplectic slice theorem. Slice theorems are basically telling you the following. So you take like a closed orbit for the action of a reductive group, and you see how your action looks in the neighborhood of this orbit. Now, in our situation, so when lambda is Zariski generic on Kerr delta, this fellow Q underlying is going to be this one loop. And when you have one loop, then the G action on the corresponding representation space has invariance and this invariance, they don't contribute to Hamiltonian reduction, so when you reduce the action, you will still have a factor which is a line. And so the singularity is not isolated. So that's a geometric reason. Unfortunately, it takes quite a lot of work to actually implement this kind of argument. So it's kind of far. It's far from the stop called geometric reason to the stop called the box, also known as the end of the proof. But this kind of argument gives you an idea, this kind of construction gives you an idea of what you should do. So let me recall this like a useful idea. You try to reduce the study of this short wall crossing function to the case when Q has 1 beta. In this case, geometric objects that I will get are Hilbert schemes of points on C2 or more general some Gieseker varieties. Now I want to state some more maybe precise results about the about this function. And as you know, in mathematics, if you have some objects with good properties, you call it perverse. That's a convention. So, so these precise results are going to be about imaginary short-wall crossing as a perverse equivalence. All right, so I'm going to start by giving a general definition. So suppose that I have C and C prime are two abelian categories. With filtrations by their subcategories. So say C equal to C0 contains C1, contains C2, contains and so on. Stops when I have Cn equals 0. I may require the inclusions to be strict, but I don't want to do so. They may repeat, it's convenient for notational reasons. They also have a similar filtration on C prime. And suppose
n equals n.
Yeah, this is the same number. And suppose that I also given a collection of positive integers, so 0 equal to d0, less than d1, less than d2, and so on, less than dn, minus 1, I guess. So integers, which will be called homological shifts. And one more piece of notation, so I write dB CIC is a category of all complexes. With homology. In CI.
An object in C.
Yeah, there's a complex of all objects in C whose homology are in CI. In DBC.
Cn minus 1,
Yep.
they are the homological shifts of the corresponding CIs.
I still haven't told you what these shifts are for.
Yeah.
Now, there is a following definition which was given by Rukia. So we say that derived equivalence f dBc to dBc prime is perverse with respect to this data, meaning the filtration and the shifts, if the following three conditions hold. So first of all, F restricts to a derived equivalence, to an equivalence between dBCI C and dBCI prime C prime. That's the first condition. So this equivalence respects the filtration on the derived categories. Second of all, if M lives in Ci, then Hj Fm is less than 0 for j less than di. So the category Ci is homologically shifted by di. And 3, so F shifted by di, I cannot figure out whether it's plus or minus. I have problem sometimes distinguishing left and right. Gives an abelian equivalence between C mod Ci plus 1 and Ci prime mod Ci plus 1 prime. So this is abelian equivalence.
Is it if with one or two F's? Your condition. Isn't it if and non-if?
This?
Yes.
No.
No, yes, the statement of the proposition.
Well, it's a definition.
Well, I mean, to be
Ah.
complete.
So
It's a definition. Okay.
it's called perverse if these three conditions hold.
Well, if not, yeah.
Because you sent Rouquet, then I suppose that was a result.
Okay? So here is expectation. Which is setting while crossing functions are perverse. And those are while crossing functions through faces. Here is a picture. So first of all, it may be while crossing function through a single wall. Single wall is a face. Or I can have a long while crossing function. That's a while crossing function through a face which is 0. So that's the face. And I could try to depict something three-dimensional, if you really want me to. Yeah, I'm not very good on this, I'm sorry. Okay? And then, so here is a face, and here is like yet another. Yeah, I'm not very good as an understatement. Okay? So I can go from somewhere inside of here to somewhere inside of here, crossing this face. So that's an expectation. And it's proved in some contexts, but not in this one. Now, for example, So it's semi-theorem. That the long wall-crossing function is perverse with Ci. So C is going to be the category of A lambda modules. C prime is going to be a category of A lambda minus modules. And I can tell you who is Ci. So Ci is a category of all modules M such that the dimension of the support of A lambda modular annihilator of M is less or equal than 2i. And di here is equal to I. And for holonomic modules, so this dimension here is just the dimension of the support of the module. So this dimension here is just, well, twice the dimension. So this is equal to 2 dimensions of support of M.
So this is like
Dimension of support of M if M is holonomic. And this semi-theorem implies the theorem in Hasse's lecture. So theorem in Hasse's lecture follows from here. Or maybe I should say that would follow from here, because this is not yet proved in this context. And now let me return to the imaginary short-wall crossing functor, so to perversity of the imaginary wall crossing. So theorem. So for the theorem, I will need some notation. So I have theta and theta prime. So these are separated by Ker delta. And I have corresponding lambda and lambda prime. So lambda prime as usual is in lambda plus zq0. And abelian localization is true for lambda theta and lambda prime theta prime. Now the notation I need is the following. I will need the number r, which is w dot delta. And I will need the number m, which is the denominator of the pairing of lambda with delta. If this is irrational, this wall is not essential, but I can put this denominator to be equal to plus infinity. Okay? So what do we need next? So now there is a statement. There are ideals. So maybe before doing this statement, I want to finish introducing notations. So Q maybe let me use capital N, will be given by the formula, so I will take dimension of M theta V. I divide it by 2Rm. I take the integral part and I add 1, I guess, in order to make this compatible with this notation. So I will have a filtration of this length, M. And then the claim is that there are two-sided ideals. A lambda equal to J0 containing J1 containing.
Is that to write there?
Yes, Jn minus 1, J1, J0 equals 0. And similarly in the other algebra. Which equal to their squares. So gi squared equal to gi, and gi prime squared equal to gi prime, such that for Ci being all modules annihilated by gi, and Ci prime all modules M prime being annihilated by gi prime M equal to 0. And for di equal to I Rm minus 1, the corresponding wall-crossing functor is perverse with this data. And in particular, if you look carefully at numbers which appear, you see that all, so observation, so this d I is always less than 1/2 of the dimension. Because here you divide by 2Rm, and here you multiply by Rm minus 1. So this factor here is less than the denominator here. All right, so in the remaining minus 1 minute, I want to, I mean, that's of course, this statement is impossible to comprehend, but I want to explain what this means. So first of all, note that the only part of information about lambda that I need to know in all this theorem, in all the numerics, is lambda dot delta. Not only information about lambda is the value of lambda delta. In particular, what I can do, I can deform lambda staying in the hyperplane lambda dot delta is a constant. So let me draw a picture. So here is a wall. So here are my chambers. This is Kerr delta. And here I have a line of lambda. So here I have lambda. And here I have lambda prime. And I have fixed difference chi. Chi is fixed. But now I can start to move this lambda along this line. And if I move it by an integer, nothing changes. Category stays the same. But I could try to deform. So I deform lambda to a while generic point on this lambda dot delta equal to constant. And the point is that, so wall crossing functor deforms continuously, meaning that it is given by a tensor product with a bimodule, and this bimodule is covering a flat family. So because it's a derived tensor product with a bimodule, so bi lambda is a bimodule, and these bimodules form a flat family. Okay? So now what is the point of this? The point is that now when lambda is indeed wild generic, then there is only one essential wall. Then Kerr delta is the only essential wall. Well, I mean, for the wall to be essential, you need a root defining this wall to be integral on lambda. And for all other roots, being integral on lambda will define on this hyperplane, well, it will define a countable collection of smaller hyperplanes, right? In this picture, those will be points, right? And while generic precisely means that this is a value which escapes countably many algebraic subvarieties. So I can always achieve this. Now, once Kerr delta is the only essential wall, the corresponding wall crossing functor is a wall crossing functor which crosses all walls which are essential, and so it's a long wall crossing functor which is governed by the Semmes theorem. is a Longwell crossing function. Well, the semi-theorem in this case is a theorem. It's an actual theorem, it is proved. And from that, after some work, you get this theorem, so this imaginary theorem, again for lambda while generic. And after some more work, somewhat harder work, you get this imaginary theorem for any lambda. Well, lambda, n is a risky generic lambda, but that's not important. For initial lambda. So your theorem will involve some claims about the behavior of this family of bimodules and also behavior of a family of ideals. And you could imagine that you can try to degenerate things in such a family. All right. So now that's it.
Wait. First we think, then we ask questions, then we think again.
And then we again ask questions. And
Yes, so let's think both figures. Questions? I have a question. About this Heisenberg action. So, what is the precise status? It's not constructed, or it is constructed, but it is not formally related to these translations?
so first of all, I don't think that axiomatics that would work in this case exists.
So it's not Aded-Jacobi's case, or so Aded-Jacobi has some categorical.
Well, I mean, many people have some categorical action of Heisenberg, which work in various situations. So here, in a special case, the action exists due to Shang and Vassero. In the case when you have cyclotomic rational чередник algebras. The construction doesn't generalize to other cases. And also, the construction is just a collection of functions.
So they don't have more proper.
They don't have a two-category action. Yes.
Is there a fixed and established version for your definition of Heisenberg two-category?
No. Well, I mean, there is a definition of a Heisenberg two-category, but I don't think that people know why this category acts.
In here.
And even on the cyclotomic category O.
Is there a calculus in this case? I mean, yeah.
Calculus 1, calculus 2, calculus 3. Yes, I was writing this paper while teaching calculus, yes. Yes. Sure.
No, but I mean, okay, is there any analog of Rukier definition which is like general and unrelated to this particular case?
I think so, but I mean, the difference with the Katz-Moody case is that for Katz-Moody actions, it's sort of easy to produce an action of Z2 category on whatever you want. Because before the definition of Z2 category due to Rukier and Khovanov and Lauda, there were examples. And examples of categorical actions of this category are more or less easy to produce, and there are plenty of those. There are examples of actions of the Heisenberg 2 category, but not in this case.
So they fit in some framework, but not in.
Not in this. Moreover, in the general setting here, even functions are not constructed, because the definition used by Shang and Vassero is very specific for the case that they study. However, results that they get, so they were solving a problem of very similar nature, so results that they get suggest that there is a relation between the wall crossing function, this imaginary wall crossing function, and their construction. But
So in an established Kac-Moody two Kac-Moody action, would you have automatically a two Heisenberg action?
Maybe, but even if so, this is not related to this problem, because in this problem you take this, so to say, the central Heisenberg in GL infinity, if you want to speak in this
So
language.
it's not the Heisenberg from your Kac-Moody.
No. No. In my Kac-Moody, I have a whole bunch of Heisenbergs associated to Cartan, right? But I need a Heisenberg from GL infinity, which comes from the center of GLN.
And by the way, when you say Heisenberg, is it Heisenberg or is it lattice algebra?
It's a Heisenberg. It's the longest infinite dimensional Heisenberg algebra.
Any other questions? So let's give the storm of applause to our speakers. You should know how it should be done